Alright, we're going to do a little more experimenting on the magnetic and electric fields across our primary here, a very long primary. My little Tesla tower coil, and across the microwave oven transformer secondary, which we are using as a secondary, which is of course around the primary with a rather large air gap between the two. The blue channel on my scope is hooked across that secondary and resistive load. Not sure, I can't remember what the resistor value was, but that doesn't really matter because we're looking at field effects here, both electric and magnetic. Blue channel is set at 1 volt per division. The yellow channel, which is at 5 volts per division, is just across the transformer primary coil combo. I have the coil, secondary coil, down one end of our primary, and we're going to switch it on, and we're going to watch the amount of power being dissipated across that resistor as we move our secondary towards the middle. And like I said, I'm not sure what that resistor was. I can't even see the colours, it's only a little quarter watt one. But nonetheless, we can see a rise and fall in power being dissipated across that resistor due to the voltage, RMS voltage across that resistor. So turn our transformer on. The one thing I still don't understand, we're only running at 50 Hertz, as you can see. For some reason, primary and secondary are nearly 90 degrees out of phase, probably about, well, maybe 75 degrees, something like that, and I don't know why. In this case, it may have something to do with the very high turn ratio on the secondary and the capacitance within those windings. Not sure, but anyway, we'll continue on. So with our secondary down one end of our primary coil, we have 2 volts RMS across our little load resistor there, and we have 9.4 volts RMS across our primary coil, even though our little transformer here is set at 7.5 volts, so not a very good quality transformer, but very cheap, as in I didn't pay a cent for it. Right, so we'll just move this a little ways up the coil. We can now see we have 2.56 volts RMS across our load resistor. Sorry about the light, I'll try and keep it out. The light's a bit hard when the sun's shining through the windows. So we've gone up a little in output on our secondary. We move a little more towards the centre. We now have 2.64 volts RMS across our load resistor on the secondary, and you'll see the closer we get to the centre of our primary coil with our secondary, our output power from our secondary, I'll go about the middle now, it's pretty close to the middle, goes up and up and up. So we now have 2.76 volts across that load resistor on our secondary. So once again, once we pass the middle and head back down towards the other end, you can see it starts to drop. Until such time as we get level at the end of the primary coil, and it drops down quite a lot. So the strongest field is at the centre of this long coil, and all we want to know really is whether it's the electric field rotating around or oscillating around the primary coil that's inducing the EMF across the secondary, or whether it's the magnetic fields going that way and that way, or oscillating because we're using AC, cutting through the conductive windings of that secondary that is inducing the EMF across our secondary. So yeah, but that phase shift, I can only put it down to capacitance within the windings, so I can't see any other reason why it would have it at that low frequency. So for the next part of the test, I'm going to take these two steel plates that I've cut out, and I'm going to use some double-sided tape there and stick a steel plate either side of our secondary. So just to see what happens. So a question before we go and do that, will it deflect the magnetic field cutting through that secondary, or will it enhance it? So if I put these plates on either side of our secondary, are we going to see a reduction in output power, or are we going to see an increase? So I'll go ahead, put these plates on, we'll come back and we'll have a look, see what happened. Okay, we've got our two big steel plates either side of our transformer secondary, and yes, they are steel, as you can see. So now we're going to switch on the power supply to the primary, and I have this in about the middle. It's leaning over a little bit because I didn't stick the plates on quite even, but anyway, make no difference. We're going to switch on our power supply now and see if there is any difference to what we had before. So switching on, and that is the result. The sun's a pain in the arse, I know, but anyway, much I can do about it. We have 2.68 volts RMS across that resistor, 2.64 to 2.68, so it's exactly the same as it was before. Our RMS voltage across our primary is 9.4 volts. That's the same as it was before. And the wave shape is much the same as it was before. So I have to be a little careful now because the plates are bigger than the coil, very close to my primary here, those steel plates. That's why I have this blocked up a bit, and it's slightly tilted, but nonetheless I'll try and slide it up the other end without doing any damage to anything, as close as we can get it to the other end. And once again you see we have exactly the same, a voltage drop. So putting the two steel plates on the side in this case has made absolutely no difference to the output power being put across that resistor from our secondary coil, nor has it made any difference on the input side either. So yeah, next what we're going to do is we'll take these plates back off because we know they do nothing now, and I'm going to place this back into the centre of the coil, our secondary, and then I'm going to slide a big laminated core down inside the primary coil, and we'll watch what happens across our secondary then. And yeah, who wants to take a guess at that one? We'll be back soon. Alright, so we've got a big square block of transformer laminates, and I've just numbered it 1 through to 9, so as you can see I'll give you some idea or a reference as to how far this is inside our primary. So once 5 starts to disappear, in the end it means we're starting to cut through our secondary with the core. So well, this end is going to start running through the primary secondary position there. 2.72, 2.68. that might be having some influence on things here. Just move that. So much the same as before, with our secondary in the middle, and as you can see we're running the same 9.4 volts RMS on our power supply. So we're now simply going to slide this big laminate in. Now I'll try and keep the camera on the show here. So we're just in at the start, nothing much changed there. We'll go to number 2. This is going to be hard watching the camera and doing this all at the same time. We now have 2.8 volts RMS. I'm just going to take another bite at this laminate. Okay, so we'll go up to number 3 on our core. We now have 3.6 volts and my coil has moved a little, so I'm going to slide that back and put it in the middle. Like I said, this is extremely hard one-handed. I should have set it up on the tripod, but nonetheless. Okay, so number 3 is right there. 3.12 volts across our secondary resistive load. This is getting harder and harder. Okay, so we're now at number 4. We're still pretty much in the middle. Now we've got to turn our voltage divisions down. So we have 4.96 volts across our secondary and resistor combo now. We still have 9.4 volts RMS across our primary. The phase hasn't shifted much. So now we'll go up to number 5. Okay, so we now know that that laminated core is about to start to go through the centre of our secondary there, and looky what happened here. I have to go down in the voltage divisions again. Okay, so now we're at 8.4 volts RMS across our little U-bit resistor here. We're starting to go up on our primary voltage as well, which to me is kind of showing that the current should be going down, because that transformer can only deliver so much power across our primary here. But we'll whack a little bit on the end of this video and we'll chuck a 1 ohm 10 watt resistor on our primary input. We'll have a look at the current as we slide our core material through. So we'll keep on going up to number 6. So that steel laminate will now be just on this side of our secondary coil, in relation to our secondary coil, and we now have 19.2 volts RMS across that secondary, and still the 9.6 volts RMS across our primary, but now we are 180 degrees out of phase. Interesting. Alright, so now we'll go up to 7. We'll keep on sliding it in. Okay, 7's in. So we can safely say our core is about here somewhere in relation to our secondary. Just straighten all that up again. Now I have 23.2 volts RMS across our secondary, 9.8 volts RMS on our primary. So if I had a 4-channel scope, we could be watching the current on the primary at the same time, but unfortunately I don't, so we're going to have to do that separately. But let's keep on going. I'll just give that a wiggle as I'm sliding, seems to work alright. Put that back under there. Move that back to the centre roughly. Alright, so our core is now about here. And we have 24.8 volts RMS, and we now have 9.8 volts RMS on our primary, or across our primary. And now we'll go into our last bit. I'm just going to put the camera down for this, it's a bit tricky. Okay, so our core now is all the way in, so that is now under all the windings. It's the exact same length as the windings, as it happens to be. So that was a stroke of luck really. Our secondary is roughly in the middle, pretty much. We now have 25.6 volts RMS across our secondary resistor circuit. 9.8 volts RMS across our primary, and now the phase is 180 degrees out, which may be telling me that I have perhaps the scope invert is off on both channels. So yeah, I've probably got the scope around the wrong way, because we basically have a standard transformer here now with an iron core, whereas before we had one with an air core. So that's our measurements: 25.6 volts RMS across our secondary, 10 volts RMS across our primary. I put the camera down, I'm just going to slide that core straight back out, like so. Everything is still in the same position, still in the middle, nothing else has changed. And now we have, just wind them up a bit. Oops. Now what happened? Wrong way. Ding-a-ling. Okay. So without the core we have 2.6 volts RMS across our secondary and 9.4 volts RMS across our primary, and the phase is only, what have we got, 1, 2, 3, 4, 5, 1, 2, less than 90 degrees out. So we know the secondary has to be trailing the primary. Can't be in front of it, that means we'd be producing power before it got any. So our phase orientation must be correct. So there you go. Core makes a whopping difference. So what I'll do now is I'll get rid of our secondary, and I'll put a CVR on the primary. We'll have a look at the current flowing through this coil without the core, and then we'll slide the core straight in all the way and have a look again. Okay, we're set up to go. 10 watt 1 ohm resistor, and the ground of course is common with the other ground. This clip lead just wouldn't reach over there, so I've just left it as it is, but all common. The blue channel is across our CVR, and the yellow channel is still across our transformer. So we'll switch her on, and that is what we have. We have 2.24 volts RMS, which means 2.24 amps, and 9.2 volts RMS across our primary still. And it's just started raining, and it is pretty close to the middle of summer here. So that's what we have without the core. I won't stop the camera, simply set it down, and I'm going to slide the core straight in all the way. Okay, so our core is in, and we can now have a look at what that did to our voltage and current across the primary coil and the current flowing through it. So now across our CBR we have 960 millivolts, which is 960 milliamps at 10 volts RMS across our coil CBR combo. So by sliding the core in, we're consuming far less power, which means that this coil here now is dissipating far less power than it was before, but as we've seen previously, we get a lot more out of our secondary with the core in there. So even when there's a big gap between the primary and the secondary, having the core in there, well, it basically now produces more power with the core in there than it does without it, whilst consuming less. So now we're dissipating less power from our primary, and we dissipate more power from our secondary when the core is in there. So there you go. In this case, having the core is far more efficient than not having the core. Right, that's it for this test. Long enough, probably boring enough, but there you have it. Dissipate far less power from our primary with the core in there, and we dissipate a lot more power across our load resistor from the secondary with the core in there. So we can say that this kind of transformer setup in an air core design is just crap. Alright guys, thanks for watching, and we'll see you next video where we're going to have a look at the magnetic fields inside. And we're simply going to slide a small inductor down in the tube and see what happens as it passes through the centre, see if it has the same effect as we get from our secondary on the outside. Till next time.